I'm going to show you data collection and data processing for an experiment where we slide a sled down an incline. This is almost the same thing as what you're going to do in the report, but instead of changing the angle, I'm going to change the mass. Let's try to get the mass evenly distributed. I'm going to use sand. I've sand in this one, and then pour sand in. That's also why I put something on the front here, so no sand hopefully falls out during the experiment. So let's try and see how it works. I realize you can't probably see this very well, but still I have the data measurements up here. So, and the angle is constantly the same, it's going to be 25 degrees. So I'm going to run like this. This, and then to make room for the data here, and then this first one had a mass of the first one here had a mass is equal to 41.72 grams. Okay. Now let's pour a bit of sand. That was far too much. Bit of sand. Try to evenly distribute it. Okay, let's see. And we'll take the next measurement. Distance as it should be. Yep, I just tapped it a bit before because I don't want the sand to spill all over. And let's see. Yes, it should be. And then the mass is equal to 53.47 grams. I'm going to take 4 more measurements, but I will speed through those with video editing because it's not that exciting to see the same thing again. Okay, totally. Okay, now I'm going to show you how to create the different graphs which are interesting to look at according to this experiment where we have the sled sliding down an incline. And I have here my last data set, and the first thing you're asked is to create 2 specific graphs and then take a screen grab of those. So I'm going to press over here at the y-axis. It says position. It has the position for my last data set. I'm then going to ask it to give me the positions for all my different data sets. And of course, we didn't let go of the sled at the same time, so they're not going to look similar when they, at what time they was let go. That's totally fine. But the important thing is we want to zoom in so we have all 6 graphs here. And in your data, they're not going to have the same gradient. This is because all my experiment was at the same angle. So I can do like this, I get this area, and then we have the positions for all 6. Then you can screen grab this. Before you do that, I want you to get down here edit graph settings, I'm pretty sure it's called in the English one, and then give it a title. So here it is time position, and then you can write all 6 measurements or something similar. Okay, and then when you screen grab, remember to get everything here. Then the other thing we want is all the velocities. So that's the second one here. So turn off the position, turn on the velocity. For all 6 datasets. You have something like this, and again, we are interested in this area. So I zoom in on it, and then I need to change the title. So go back to edit graph settings, the last one when I press this one, and then it's now time velocity, all 6 measurements. And now I can again screen grab. Okay, now we get to the graphs, individual velocity graphs. So what we have to do is we take them one at a time. So I have the first one here. Then first we need to change it in here to points instead of lines. And then zoomed in on this area here. And then use curve fit. I'm pretty sure it says in yours. And then a linear. Move this box over here. And again, we also want to zoom in on this area here. And now remove the box so it's not at the same place. So we can see the motion and we can see the gradient, and the p-value is not really interesting, and you can see something about if the data is following. And again, we need to change the title. So this is time velocity, and then I need to write what the mass is for this one. So m is equal to 41.72 grams. Of course, you have to write angle and then equal the first one is 20 and then 25 and so forth. But in my experiment, it was the mass achieved. So you have to screen grab these one at a time and then put them in one at a time in the document. I'll just quickly show you one more. I'm not going to show all 6. But when we're finished with this, we can start by zooming back out so we're not zoomed in at the wrong area. Remove the linear and then press the next one and remove the first one. And then we have an interesting area here where we use curve fit. It's linear. And it's also that area which we want to zoom for. And then we also want the title changed. And now I need the mass to be 53.47 grams. So that's how you get the 6 individual graphs, and then the m value is going to be the gradient, which is the one value for acceleration. You can also see in this meters per second, which is meters per second squared. When you screen grab, start all the way up here, end all the way down here, so we also have the names of the 2 axes. Yes. Okay, now that we have our graphs which show the acceleration by having the velocity on the y-axis and time on the x-axis, we can use that information to calculate some different forces. Some of them we calculate from the data, some of them we calculate from the data for the mass of the slit, and then we can find the friction force at the end. So firstly, we want to find the net force. That is also the observed force the one that is according to what we can observe in the experiment, because that is what happens to the object when all the forces is added up. So that is equal to the mass times the net or observed acceleration. And that acceleration is the one we found in the experiment. So I'm doing this for the second data point, where the mass was 53.47 grams. So I changed that to kilograms, and I times it with the acceleration found in the experiment, 2.117, and that is Newton per kilograms. We can also use meters per second squared, but Newtons per kilogram works great right now because then we get the answer Newton. And the answer is going to be 0.1132 Newton. 4 significant digits, because we had 4 significant digits on both of these values. Then the second force we can find is the normal force, which is equal to the force being pushed back because the sled is on the surface. And the normal force is equal to the mass times gravitational acceleration, and then because it's an incline, it is time the cosine to the angle. So the mass is still the same because it's still the same sled with sand in it. Acceleration is 9.82 newtons per kilograms. Again, I use the newton per kilogram unit. And cosine, the angle in my experiment, was 25. And then the answer in this case is 0.476 Newton. Enough room. Okay. If there is a normal force, which is the normally if it's a flat surface that is equal to or but opposite direction for gravitational force or gravity, in this case gravity is the normal force, the perpendicular force, and then the parallel force to the incline, which is the push force, because some of gravity is pushing the sled down. And the higher the angle is, the more is being used to push it along the incline. So that is almost the same formula as before. It's just sine to the angle. And then again, we have exactly the same mass because it's still the same sled we're looking at. And gravitational acceleration is 9.82. And sine to the angle. And that is going to be 0.222. In these two, I only have 3 significant digits because we only have 3 significant digits on gravitational acceleration. And then the last force we can calculate is going to be friction. And friction is the force that is trying to stop the sled. And we have the force that is pushing it forward, and we have the force that is where we observe how much the sled is being accelerated. And therefore, the friction is going to be the push force minus the net force. All of my forces in this case I have calculated as scalar, so that's why we have the minus in the formula. Otherwise, the friction force would be negative, and therefore we could net force is equal to friction plus push force. So we need to switch these two around if we want to do that. But I'm calculating everything with positive values because I'm only looking for the magnitude for the forces. You can do either in your own report. The push force is 0.222 Newton, and the net force was 0.1132 Newton, and it's 0.109 Newton. 3 digits after the comma, 4 digits after the comma. We need to round to 3 digits after the comma because that's the one with least digits after the comma after the point. Yes, that was what I want to show with the formulas, and then we get to the last part. To do the last part of data processing, which is to make the linear function. So, without connecting and with this data table open, we have to write our f normal as our x values and our f friction as our y values. So I'll just start by changing to f normal. You can also do an underscore if you want to, and that's in Newton. And then f friction. It's also in Newton. And then I just quickly have to insert the values. Let's see. And unfortunately it is, oh wait, can I do, I'll just quickly do something. Yeah, like this, so. Series. And so why is it? Oh, we might have, of course, changed it to comma because that is the Danish version of the program. Does that? Okay, so now I have my 6 data in here. And then I want graph options, use curve fit, but I have to change it to proportional. Because what we expect to happen is if the normal force is 0, then the friction force should also be 0. I also need to change some things about this. I have to give it a name. And it's going to give me coefficient of kinetic friction. And then I always want to be able to see 0 on this graph because that's kind of an interesting point. And then I'm also going to move it a tiny bit more just so I don't have this point exactly in the corner. So here you can see the proportional function I made. You can also see my points actually look like they are not necessarily proportional. They are a bit more linear. If I started with a positive b value here, I'll probably fit the points more. That shows that my coefficient of friction is higher at the beginning and becomes lower and lower and lower. And that probably has something to do with that the mass I included, the sand, is moving a bit while it's sliding down. And if it's moving, it is becoming slightly weightless at some points, which is going to increase the possibility of acceleration and therefore decrease the friction force, the y value. And more sand, this effect is probably happening a bit more. That's not going to be anything you can use in your argument. You have to talk about the angle. But because the formula for friction is the coefficient of friction multiplied with the normal force, I can then use this formula here where friction is on my y-axis, the normal force is on my x-axis, and therefore the gradient is going to be coefficient of friction, and because it's something in motion, it is the coefficient of kinetic friction. And you can also see that it has no unit because it's Newton divided with Newton, which the program doesn't know, it means no unit, but that's what it means. Okay, this was the last part, so now I have shown you all the important four parts of I want to show you, so you hopefully have all the information you need to actually do the experiment. I'll do the report.